In this video, we're going to deal with the ideal gas law. Now, an ideal gas is a gas that is at low pressure, particles are moving freely, and with enough speed. So we're generally considering normal conditions, real gas will behave like an ideal gas, but under extreme pressure or extremely cold conditions, a gas starts to behave more like a liquid than a gas. The ideal gas law is PV equals nRT, and R is given to you in your data booklet, so it's provided for you here, and they give you the complex units. So it's 8.314 kilopascals times liters over mole times Kelvin. Now I've shown this a number of times, but R, if we got rid of the number, is equal to kilopascals, which is pressure, times volume over mole times temperature. And this rearranged is the same formula as this. So PV equals nRT. So as long as you know the complex units for R, you could come back and figure this out. Question 4 says, predict the chemical amount of methane gas present in a sample that has a volume of 500 milliliters at 35.0 degrees Celsius and 210 kilopascals. Now, with this, all of my units need to be in kilopascals, liters, moles, and Kelvin. So I'm going to change this to 0.500 liters. This needs to be in absolute value, or the absolute value temperature. So that's going to be 308 Kelvin. This is already in kilopascals. We want to know the chemical amount, which is the name for molar amounts. So that's the chemical amount as opposed to like mass or volume or something like that. So I want to calculate for N. So if I've got PV equals nRT, N, to solve for it, I need to get RT to the other side. So it's going to be PV over RT. And my pressure is 210 kilopascals times the volume of 0.500 liters. And my R is 8.314 kPa times liters mole times Kelvin. And my T is 308 Kelvin. Now, just a side note, I'm always showing all my units because I like the cancellation. So I have kPa divided by kPa and liters divided by liters. I have Kelvin times mole per Kelvin here. So the Kelvin is 1 over mole per Kelvin, so the Kelvins also cancel out. This is going to leave me with 1 over mole, which is what I want to calculate. So putting this into my calculator, I've got 210 times 0.5 divided by bracket 8.314 times 308, close bracket, and it gives me a value of 0.041 mole. I only had, how many significant digits did I have? So I should be able to take this to 3 significant digits, so I'll put a 0 on the end of that because there's a 0 here. So this has got 3 sig digs. The 4, 1, and 0 are all significant. The zeros in front are placeholders. This is also equal to 41.0 millimole. Okay, so for question 5, it says, what volume does 50 kilograms of oxygen gas occupy at a pressure of 150 kilopascals and a temperature of 125 degrees Celsius? Well, 50 kilograms is 50,000 grams, so that's a large mass. The molar mass of oxygen is 32.0 grams per mole, because each oxygen atom's atomic mass is 16.00. So we've got 2 of them, so it's twice that number. So N equals mass divided by molar mass. So I've got 50,000 gram divided by 32.00 gram per mole. And so I've got 50,000 divided by 32 gives me an answer of 1,562.5 mole. I'm going to keep that whole number, so I'm not going to round off at this point. I'm going to round off in my very last step. So now I've got N, P, and T, and we want V. V is going to be equal to nRT over P. So my 1,562.5 mole times R, which is 8.314 kPa, times liters over mole times Kelvin. And that is also times temperature, which we said is 125 degrees Celsius. So 125 plus 273, this is 398 Kelvin. So we have to have that unit agreement. So 398 Kelvin divided by pressure. And pressure here is 150 kPa. So I'm going to just double check to make sure I didn't make a mistake with my units. I've got mole and mole, kPa, kPa, liters are going to be what I'm left with, and I've got Kelvin and Kelvin. So all of the units are going to cancel each other out to leave me with liters. So my volume in this case, I'm going to use this whole number, so 1526.5 times 8.314 times 398 divided by 150 gives me a volume of 3, and how many sig digs do I have? I have 2 sig digs. So this will be 34 times 10 to the 3 liters, or 34 kiloliters. So that's how you handle these sorts of questions. If you're given a mass and you know the kind of chemical that it is, so you know its chemical formula, you can always calculate the N, which then can be used in the PV equals nRT. So there's a real nice connection between chemical amount, volume, and pressure and temperature, and it all goes through your R value. So hopefully that helps you out.